The next lecture is going to be the fundamentals of Epr spectroscopy, and our speaker is Art Vanderest from Brock University, which is located in St. Catharines, Ontario. Now, Art gave such a lucid and clear lecture 2 years ago that he asked him to come back and give a lecture today. But we've changed the format a little bit in that a couple of years ago I had about 1.5 hours or more to talk about the fundamentals of Epr, and we're going to be limited to 1 hour. So much of the material of the practical aspects of, in this case, Epr, is going to be covered in the practicals, and I'll be running the Epr practical number 1, basic Epr section. So the upside of this is that if you have questions, you can please ask during the lecture or during the question and answer period. But more importantly, all of us are going to be around all week. And if you have questions that say formulate even afterwards, please see us, ask us during the practicals, and we'll be at social hours and things like that. So it's going to be up to you to ask us those questions because we're just dying to answer them. So with that part, Epr.
All right, thanks, John. So we've also got a new microphone, so hopefully it's all easy to hear me and so on. Yeah, so we're going to talk about Epr. This is, of course, a huge, huge topic. And so our goal here, basically, in this first lecture is to just lay some groundwork for things you're going to see in the practicals and so on, and maybe lift some of the mysteries of why a spectrum looks a certain way and things like this, right? So a lot of this is a little bit superficial, but as John says, I'll be around and the others will be around the whole week, and we would be happy to discuss things in more detail later. All right, so just to set the stage here, Epr, of course, is magnetic resonance, and we look at unpaired electrons. And of course, this is really, really useful for transition metals, which often have paramagnetic states, right? But in addition to that, we can also look at free radicals, and so radical enzymes are also widely studied using Epr, and other systems in which free radicals are generated. What you can also look at with Epr are excited states. And I'm not going to have time to really touch much on this, but if you can shine light on a molecule, for example, and excite it into, say, a triplet state, which is paramagnetic, then you can also study this by Epr methods. A real, well, at the same time, a drawback and a real advantage of the method is that it's only sensitive to unpaired electrons. And so if we have a complex or a molecule which is diamagnetic where all the electrons are paired, then the method is completely blind to it. And so, of course, that leaves then a whole group of molecules out there, or really almost all actually, which can't be studied directly using Epr. But on the other hand, it's a real advantage in that if you have a system which is made up of something, some big complex protein with a paramagnetic center in it, you can selectively look at the paramagnetic center and not have to worry about all the rest of the stuff around it, right? Okay, so this really comes into play then in bioinorganic chemistry and studying bioinorganic systems. If we're looking at a metalloprotein, usually the metal center is where all the action's happening. This is usually the catalytic center of the enzyme, and the thing that we really want to understand. We're interested in the mechanism of how it functions and so on, and Epr data can really help in that regard. And as I say, what's useful here is that with Epr, we're then blind to all the rest of the protein, which with many other spectroscopic techniques gets in the way, right? So for example, if we were going to use infrared spectroscopy and try and look at vibrations, you've got the vibrations of the whole protein and the active center somewhere buried underneath this massive background signal, right? And so as we'll see as we go along, there are kind of two types of paramagnetic states which have quite different Epr properties. There are S = 1/2 states, which things like copper 2 would have a S equals 1/2 state. And then there are systems where we have high spin, where the spin is greater than 1/2. And their EPR spectra are, as I said, quite different. Anyway, and so we can study these using EPR. Right? All right, so what I'm going to do here, the way I've structured my lecture today, is to start by talking a little bit about the basics of the EPR experiment, because compared to other forms of spectroscopy, there are things we have to do in EPR which are a fair bit different. And it means that the spectra that you look at are different, say, from a UV-Vis spectrum, which is relatively easy to understand. Here's the absorbance, there's the wavelength, everything's cool. In EPR, the spectra look quite different, and for beginners, that's often a little bit confusing. So we're going to go through just some basics of how the experiment works. The other goal here is also to show you things you have to watch out for if you're running an EPR spectrum. All right, so there are parameters that need to be set, and I just want to point out which ones are important and what you have to watch for, because you can often run into problems trying to run an EPR experiment if you're not aware of these things. Anyway, and then we'll talk a little bit about what sorts of information you can get from an EPR spectrum. We'll talk about G anisotropy and hyperfine couplings, and then I'll touch briefly on some high spin systems and introduce you to Rhambo Grams, which are useful for analyzing these sorts of spectra. Here are a bunch of books which are good if you're a beginner and give you kind of an introduction to things. One I really like is this Biomolecular EPR Spectroscopy by Hagen, which is really starts from the idea that I'm a biologist and I'm not really very good at math and I don't know anything about physics and all this kind of stuff, and what does my sample look like and where do I put it in the spectrometer and so on, but he gradually builds on that, and the last half of the textbook actually gets really quite heavily into the quantum mechanics and stuff, but he doesn't sort of throw it out at you right at the beginning and scare you away. Another standard work is Weil and Bolton. This is much more advanced in terms of the theory and so on, but it's also very heavily focused on inorganic systems, and so from that point of view it's quite good for this audience anyway. There's a lot of practical stuff in this book by Brustolon and Giamello, and then a plug for my own work. So John and I wrote a chapter in this book on molecular biophysics for the life sciences, and much of today's lecture actually is based on the chapter in this book. All right, so let's get down to business here. So starting from the very beginning, if I have a single electron, it of course has a spin quantum number s, which is equal to 1/2, and it has two states associated with the orientation of the spin, which is m sub s, which can be plus or minus 1/2. And if we put our electron into a magnetic field, then these two levels split in energy, and the energy gap here is given by this free electron G value, which is a constant, the Bohr magneton, which is a constant, and the strength of the field. And of course we can then do spectroscopy on that and try and cause transitions, look at the absorption between these two states, right? And so the first question is, so what kind of energies are we talking about? And if I take, if I write h nu is equal to g beta b0, and then just divide through by h, I get a constant g beta over h, and that tells me the relationship between the frequency I need and the field. And the value there is about 28 gigahertz per Tesla, right? So if I've got a field which is on the order of a Tesla or something in that ballpark, then I'm going to have frequencies in the megahertz range, or gigahertz range rather, which is in the microwave region of the spectrum. So what we're doing is microwave spectroscopy on our unpaired electrons. So that creates a whole bunch of challenges. So normally if we do an absorption experiment, we have our sample and we have a source. We shine our electromagnetic radiation through the sample and we try to measure how much of that has been absorbed, right? So we measure the intensity before and after the sample, and then the absorbance, of course, can be derived from the ratio of those two, right? If we try to do that in the microwave region of the electromagnetic spectrum, we run into issues. And the issue is basically that the difference between I and I0 is incredibly small. And so we have very, very little absorbance actually taking place. And so if we try to do that for an EPR experiment, this is really not technically feasible to do things this way. If you go to really high magnetic fields, then it can be done this way, and there are a few spectrometers out there that do this. But in general, this basically does not work very well because the absorbance, the amount of absorbance is really, really low, and so it becomes hard to detect. So there are basically two things that we do to get around this problem. The first one is that we use a resonator to detect our signals. And the basic idea of the resonator is that it's some kind of a cavity, and there are different designs and so on that can be used. But the idea is that I bring my microwaves into this cavity and I set up a standing wave so that there's no traveling wave going in and out. Everything is in resonance, and I have a standing wave, right? And I design the things so that I have the magnetic lines of force are close or large where my sample is, right? And so if I draw a diagram of frequency versus reflected power, there will be a frequency at which this standing wave occurs. And then if I'm measuring anything that's being reflected back out of the resonator, because my microwave is a standing wave, there's nothing moving, and so I get no reflected power at that point. And so the way we do the experiment is then to lock the frequency of the microwaves at this resonance, right? So keep the frequency fixed at that point, and then we scan the magnetic field. And when we, so that basically means we're adjusting the energy difference between our two levels, and when they match the microwave frequency, then I get this small amount of absorption, right, by the sample. When that happens, I disturb the resonance here, and it creates a traveling wave in my spectrometer. And so I can detect this traveling wave, and the point here is that the intensity of the reflected power that I'm seeing is larger than the amount that's actually being absorbed. And so what I end up doing is just amplifying the signal this way, right? And so this is a way to increase the sensitivity of the instrument. The drawback of it is that we have our fixed frequency and we're sweeping the magnetic field, and that's really different from most spectroscopies where we vary the frequency and try to find the places where the absorbance occurs. And so here we vary the field. The second thing that we do is we use a technique called field modulation. And so here's a picture of a resonator, and if you look on the outside, there's this round sort of plastic cap on the resonator, and behind that there are coils of wire which are used to create an additional magnetic field on top of the big one that we're putting our sample into. And this small magnetic field we cause to oscillate at a fairly high frequency, so typically 100 kilohertz, right? And so the reason for doing that is that if this is our absorption line, and the green here represents this oscillating field, if I detect the signal then when the main field is at this position and it's oscillating back and forth between these two levels, then I'm going to see an oscillating signal at this frequency. Or over here, I would see this one. And so what I'm doing here basically is encoding the EPR signal so I can recognize it in my detection, right? So if I know that if I'm detecting a signal and it's not oscillating at this frequency, then I know that it's noise, and I can eliminate it completely. So I can filter out everything that's not oscillating at this frequency, and that creates a huge increase actually in the signal to noise. Leads to a very, very big increase in sensitivity. One drawback of that, though, is that now I have what I'm detecting is this oscillating signal, and it's not the height of this is not proportional to the height of the signal, but it's proportional to the slope, right? So if I were up here at the top of my absorption line and I start to make my field go back and forth and look at how big the signal is, it's actually 0, right? And only here where I've got a big change in the signal as I oscillate the field do I see my signal. So what I get is a signal height which is proportional to the slope of the line rather than the line itself, right? So what we do here is we're going to scan our field and measure the height of this signal. What we also measure is the phase, right? So if you look on this side, if my field is high, my signal is going to be high, and when the field is low, the signal will be low. If I look over here, it's the other way around, right? So when my field is high, the signal is low, and when it's low, it's high. So if I look at this as a reference signal and compare it to that, on this side of the line, they're going like this, out of phase with each other. If I look on this side, they're in sync with each other. And so we multiply basically the height of this signal times the phase. If they're in phase, we call that 1. If they're out of phase, it's -1, right? And so over on this side of the line, we get this positive going peak, and then when we're up at the top, it's 0. And then over on this side, when they're out of phase, I get a negative signal, right? And this shape is approximately the first derivative of the absorption line. And so in EPR spectra, typically what we're looking at then is the first derivative, or something close to the first derivative, of the actual absorption line, or absorption line shape. Okay, so there are a couple of drawbacks to this method. One of them is, of course, that we get the first derivative of the spectrum, and probably what we would actually prefer to work with is the actual absorption line. You could reproduce that by integrating the signal. There are technical issues with doing that sometimes. But another really important one is that if I change the amplitude of my modulation, so in other words, if I go back to this figure here, if I change the range at which the oscillating field covers, then the height of my signal will change, right? So the larger, if I make that really, really small, then there's not going to be any change in my signal, and so I get a small intensity of my spectrum, right? And so in this diagram, what we've done is just gradually increased the amplitude of this modulation, and you can see that the height of the line increases, right? If you take that too far and your modulation now starts to become bigger than the line that you're trying to measure, then the spectrum that you see starts to distort, right? And you can see here, if I really take a much too big modulation, then the width of the line that I get is really a lot bigger, right? So when you're running an EPR experiment, this is really important to know how do I set that? How do I choose the value of my modulation, right? And so up here in the corner, I've got a little note saying EPR1. So if you're doing the practical EPR1, you will go through an exercise where we set the modulation amplitude for a particular spectrum. Okay, so that's the drawback. There are a couple of advantages. The main one, of course, being that we get this huge increase in signal to noise and makes it possible actually to see the signals that we're looking for. Another advantage, though, is that if I've got a line that has some kind of structure in it, shoulders and stuff like that, if you measure it with the modulation, these features become much more prominent and are much easier to see. And so if I've got a bunch of splittings or something in my spectrum that I'm trying to see, measuring the spectrum this way is a real advantage. You can see the structure much more clearly. All right, so a couple of other things that come out of this. One is an effect called saturation. And this arises from the fact that the energy levels that we're looking at are very close together, right? And so we have a really small population difference between the two. And if you work that out for a typical EPR spectrometer working at about 300 millitesla, the difference in population divided by the total population of two spin states is about 1 in 1,000, right? So 10 to the minus 3. So essentially we have a situation like this where we've got two levels which are almost equally populated, and we're going to try and then measure the absorption between them. So what you can see here though is that depends on temperature, right, Boltzmann factor. So if we go to low temperature, this difference will get a little bit bigger. But in general, we still have this problem that the two levels are really similar in population, right? And so if I start off with my system in equilibrium with this difference in population, if I turn on my microwaves to try and measure the absorbance, I'll start causing absorptive and emissive transitions between the two, and within a fairly short period of time, I equalize the two populations, and now I have no more EPR signal, right? Because the populations are equal, and I have equal probability of absorption and emission. So that effect is counteracted, though, by the tendency of the spin system, right? If I were to start now with my levels equally populated, if I just leave the spin system sitting there, it will relax back to my original state, right? And so there's always, in any EPR experiment, there's a balance going on between the tendency of the microwaves to drive the system to here and the relaxation taking us from here back to here, right? And so that has a really important bearing on how much microwave power I can actually use in the experiment. Because if I have too much, I'll wind up over here and I get no signal, right? Okay, so there are two effects. So one is the temperature, which will, if I go to lower temperature, that will cause the population difference to be bigger, so my signals will be bigger, and that's always a good thing. And so if, here I've got, this is plotted 1 over temperature, right? So moving to the right means the temperature is going down, right? So as we go down in temperature, the signal will increase, and at higher temperatures, this follows the Curie law, so it's a straight line. But when I get to quite low temperatures, the relaxation will slow down, right? So we have a greater tendency for the signal to saturate, and our intensity will drop off, right? If we're not careful. And then the other thing is the microwave power, right? And so if I increase the microwave power, I can see more absorption and so on. But again, if I go too far with that, I get into this region of saturation, and eventually the signal will, if I put the power really high, then eventually I can completely obliterate it, right? And so both of these effects are very important. The temperature that we do experiments at can be really critical. And it's important to know, or to be aware that, if you have the wrong microwave power, you can also not be able to see the signal, right? And again, so in EPR1, there will be a couple of a demonstration of both of these effects. Okay, so anyway, bottom line is, if I'm doing an EPR experiment, there are a bunch of things I have to optimize. I have to optimize the power, the temperature, and my modulation amplitude, right? And those will be different for any given sample, right? And so it's just important to know how to do this, and in the practical we'll show you some techniques that you can use. So here we're talking about bioinorganic systems, so we're dealing with transition metals, and it depends a bit on the metal, but in many cases we need very low temperature to actually do the experiment, right? And so if we're working at low temperature, it means we've got a frozen sample where the motion of the molecules is locked in. And when you do that, that has really important consequences for the shape of an EPR spectrum, right? And so what I'm going to do for most of the rest of the lecture then is show you how that behaves. So the first thing is that if we have an electron which is not a free electron, like I talked about at the introduction, but rather is bound in a molecule or on some atom in a molecule, then the we have the same expression, but we have this G factor then is shifted a little bit. And this is a result of the contribution from orbital angular momentum to the overall angular momentum of the electron, right? But the bottom line is that instead of having this constant, this free electron G value, we get a G value which is shifted as a result of the fact that the electron now also has orbital angular momentum because it's in an orbital, right? And so just as an example, if we look at two transition metals, copper 2, in a copper salt, we get a value of 2.13 rather than the free electron value, which is 2.0023, right? Or titanium is a little bit less, is 1.96. So the G values typically are around 2, but they're different for different ions in different environments, right? So where the fact that we were dealing with frozen samples usually comes into play is that these G values, so the position in the spectrum where the signals will occur, depends on the orientation of the molecule in the magnetic field, right? And so in order to describe that, we have to use a tensor, so a matrix of numbers, rather than just a single value. Instead of just a single G value, we now have a matrix. And that's characterized by three axes which are fixed in the molecule. And we have three principal G values, which are usually labeled GXX, GYY, and GZZ. And then if I have the molecule in some particular orientation, the observed value can be derived from these three principal values and the orientation of the axes, right? So normally, of course, we're dealing with a sample where we've got a random distribution of orientations. It's a solution. We haven't done anything to particularly orient the molecules. And so what we see then is the sum of all possible orientations. And so the G value for the different molecules in our sample will all be different, right? So we can break things down, though, into some characteristic situations. And it depends on the relative sizes or relationship between these three principal G values. And this applies actually to any quantity which is orientation like this and can be described by a tensor. So the simplest case would be if all three values were the same, then we would refer to the system as being isotropic, right? And we would have an isotropic G value, and that corresponds to a molecule which has tetrahedral or higher molecular symmetry, or the environment of the unpaired electron should have this symmetry. The other case is that we could have two of the values the same and one different, right? And this is referred to as axial symmetry for the tensor, and occurs when you've got a threefold or higher rotation axis in the local environment, right? But less than tetrahedral symmetry. And there are two cases. We could have XX and YY be the same and Z different, or Y and Z could be the same and X could be different. And then finally, if all three values are different, then we have rhombic symmetry of the tensor, and the molecular symmetry would be then, its highest symmetry operation would be a twofold rotation axis. Okay, so what we can do then is, in the computer, we can calculate the spectrum that you would expect, the EPR spectrum, for those different situations. And so you wind up with these four characteristic line shapes that can occur. If the system is isotropic, then you just get a line, just an absorption line, and centered at this isotropic G value, so the average G value. If we have an axial system, if the G value which is different, so this is when we have two the same and one different. If the different G value is larger, then you'll get a peak on the left and this positive negative feature at higher magnetic field. If the relationship is the other way around, if the two G values which are the same are larger, then you get this shape where the positive negative feature is on the left, and then we get a negative going trough on the right-hand side. And then if we have a rhombic system where the three principal G values are different, then we get this line shape, and you can read the G values basically straight off of the spectrum, or at least you can read the magnetic fields and then convert them into G values. Okay, so, but anyway, these are the basic shapes that we see in an EPR spectrum where the G values are possibly different. So it's possible to calculate the G values using perturbation theory here, and these are the operators for the angular momentum and wave functions. This, of course, can be a relatively complicated calculation, but it is possible to use ligand field theory and to work out these wave functions as the d orbitals and carry out this kind of calculation. As we just heard in the last lecture, though, that we shouldn't take ligand field theory too literally, that the numbers that will come out of that shouldn't be or should be used with caution. And so if you do this calculation using ligand field theory, the G values that you actually calculate are probably not very, or usually are not very accurate. But you can use this to understand the shapes of spectra and how they relate to the geometry of a metal in a complex. Right? So I don't have time to really go through this in much detail, but just as an example, if I have a square planar geometry, if I plug in the orbitals that I would expect from ligand field theory, we would say for a copper, if we in a square planar geometry, the unpaired electron should be sitting in the dx squared minus y squared orbital, and the equation I just showed you would predict that gxx equals gyy and should be greater than gzz, and we would come up with this, should be less than gzz, and so we come up with this shape. Right? On the other hand, if we go to a trigonal bipyramidal system, the unpaired electron would now be in dz squared, and if you go through this operation, the equation would predict that gzz now would be lower, and x and y would be equal as well, and so we would get this particular shape here. And then if we've got some kind of intermediate geometry, then the unpaired electron will be in some mixture of these two orbitals, and so we would wind up with a rhombic spectrum. And this correlates very well with the known geometries, right? So if we take ethylene diamine, we get a square planar complex, we get this line shape. If we use phenanthroline with a chlorine, we get this trigonal bipyramidal structure, and the shape of the spectrum matches really well with that. Okay, so anyway, the G value is the first parameter which determines EPR spectra. The other interaction which is extremely important is hyperfine coupling. So where the unpaired electron interacts with nuclei which have nuclear spins in the vicinity. And what this does is for each of the m sub s levels, so for each possible orientation of the electron spin, the nuclear spin can take on different possible orientations. And so if we had say a nitrogen next to our unpaired electron, it has a nuclear spin of 1, and therefore 3 possible orientations of its nuclear spin. And so the energy levels for the electron get split into 3, right? And so now we would have 3 possible transitions that can occur for each of the 3 possible orientations of the nuclear spin, right? Okay, and so basically the pattern that we see, if we have a single nucleus with a nuclear spin I, then we get 2I plus 1 lines of equal intensity in the spectrum, right? So if I have a proton spin 1/2, 2I plus 1 equals 2, I get 2 lines of equal intensity. If I go to spin 1, 2I plus 1 now is 3, and I get 3 equal intensity lines, right? So that for a single nucleus, then, that's pretty straightforward. We get these splitting patterns, and you could just basically read off what the nuclear spin is from the number of lines and could figure out which nucleus the electron is coupled to, right? Things, of course, are not that simple, and so we know that, for example, if I have a methyl group, I've got 3 equivalent protons, and so I can have equivalent nuclei that are in symmetry-related positions, and so the number of hyperfine lines that I see then is 2n, where n is the number of nuclei, times I plus 1, right? And then if I've got groups or several groups of nuclei, so a couple of methyl groups and some nitrogens and things in my molecule, then the number of lines is the product of 2n times I plus 1 for each nucleus or group of nuclei, right? And so I would have 2n1 I1 plus 1 times 2n2 and so on. And that number can become very large very quickly, right? So you can take a relatively simple organic radical and come up with easily 1,000 lines in the spectrum, right? And so that can make the interpretation of EPR spectra sometimes quite complex, especially if for very small molecules. In addition, the hyperfine coupling is also orientation dependent, right? So there are actually two contributions to this coupling. One is called the Fermi Contact, and basically arises because our unpaired electron has a certain probability of being actually inside the nucleus of any given atom, right? And so the size of the splitting depends on the spin density at the nucleus that we're looking at the coupling from. There is another term, though, which arises from the dipolar coupling. So basically each of the spins feeling the magnetic field around the magnetic moment, right? So we have an electron magnetic moment, which creates a field around the electron, and the nucleus also has a magnetic moment with a field around it, and those two fields can interact. And so that interaction is orientation dependent and goes with this 3 cosine squared theta minus 1. If you stare at that long enough, you'll see that if I make theta equals to 0, that number is positive, and if I make it 90 degrees, you get a negative value there. So the sign of the dipolar part of the coupling changes depending on this angle theta, which is the angle between the field and a vector between the nucleus and the electron. But anyway, the important takeaway here is just that the dipolar part here is orientation dependent, and it changes sign depending on the orientation, right? So what happens with hyperfine couplings is that our overall coupling that we observe is the sum of these two. And if they're of similar magnitude, then for some orientations they will cancel and the overall coupling will be small. And then for another orientation, they will be large where the two signs are the same, right? And so if I look at an EPR spectrum of a solid or a frozen solution, then for some orientations I should see we'll see a large splitting, and for other ones the splitting may not be observable, right? So as an example, here's the EPR spectrum of azurine with a copper 2 in it. And what we see is that on one of the G factor components, right, so the GZ component, you can see 4 peaks due to the hyperfine coupling to the copper nucleus, right? So the copper nucleus has a spin 3/2, and so this part of the spectrum gets split into 4 due to the hyperfine coupling. In this part of the spectrum here, the X and Y components, we don't see that splitting because the two contributions to the hyperfine coupling cancel each other and are weak there. And this is a really typical situation for many metals, is that one component of the spectrum will show hyperfine coupling and the other one will not. Right? Okay, so as we also saw in the last lecture, you can see hyperfine coupling to ligands, and this can be really useful when looking at proteins. So here is just an example of that. So here's a nickel superoxide dismutase with its nickel center, and it has an axial histidine ligand. And you can see on one of the components here of the G tensor, we can see it's split into 3 lines due to the coupling to the nitrogen, right? On the other two components, we don't see any evidence of the nitrogen coupling, and that's again because these two contributions to the hyperfine coupling cancel for these orientations. And so you can use this, for example, to identify the nature of ligands around metal centers, right? So if we knew nothing about the structure here and took this spectrum, we would immediately know that the nickel is being bound by a nitrogen, and they could then guess that it probably is a histidine, right? Okay, so those are the types of spectra that I've talked about so far. All apply when we have a spin 1/2 system, right? So where the overall spin of the unpaired electrons is 1/2. If we go to a system where there's more than one unpaired electron, then we can have a total spin which might be 1 or 3/2 or 5/2 or something like that. So something larger than 1/2. Under those conditions, the unpaired electrons can interact with each other, and the spin-orbit interaction as well alters the energy levels of the system, right? So, and leads to a splitting of the m sub s levels, right? And so, for example, if we have spin 1, then the 0, -1, and 1 levels get split apart in energy, right? If we have half-integer spins, then we get pairs of levels for the two, or for m sub s levels, which have the same magnitude but opposite sign, right? So we get a pair of levels, for example, here with m sub s is plus and minus 1/2, and then a pair of levels for plus minus 3/2, and so on. So if I had a 5/2 system, then we'd have a pair of levels that m sub s is plus minus 5/2. So this splitting of the m sub s levels, I think, as you can see, would have a very, very big impact on the EPR spectrum, right? And so it's important for us then to talk a little bit about what that effect is. So if I have a half-integer spin, then I will have two levels which are plus minus 1/2. And if I put them into put the system into a magnetic field, then I essentially get the same diagram which I showed you at the beginning for a single unpaired electron, right? And so for this pair of levels, everything is basically the way that we had before. But I also now have higher levels here, which are, in this case, plus minus 3/2, and I could have more if the spin were higher. And because the m sub s here is a larger value, the slope or the dependence on the field is higher, right? And so I can cause transitions between these levels, but they will occur at much lower field than where the transitions for the plus minus 1/2 levels would happen, right? And so the upshot of all of that is first of all, that for systems like this, then I expect to see a spectrum which is going to be much wider than what I would see with spin 1/2, because I have these transitions associated with the additional levels that I've got, and they typically will occur at much lower field or correspond to much, much higher G values, right? The situation is even more extreme. Well, actually, I guess I should point out here that in EPR1, again, you'll be looking at a high spin system and seeing this effect. Okay, where we really run into difficulties, though, is if I have an integer spin. And if the separation between the levels here is much larger than the interaction between the electrons and the magnetic field that I'm applying, then the separation between these m sub s levels will be much, much larger than the energy gap that can match my microwaves, right? So, these are drawn for a particular set of, or strength of this so-called zero field interaction. And if at X band, this would be the size of my microwave energy, you can see in this diagram, there's no pair of levels that match this energy gap. And so for integer spins, even though my system is paramagnetic, it becomes essentially impossible to see the EPR spectrum. So there are ways that this can be done. I'm not going to talk really much about this, but if you change the orientation of the magnetic field in the resonator compared to the external magnetic field that's being applied, in some cases it is possible to detect signals from these systems, but in general, integer spins of transition metals, or states with integer spins in transition metals, are very difficult, if not impossible, to detect by standard EPR methods. Right? Okay, so how do we describe this interaction? This is known as the zero field interaction because it occurs, of course, at zero magnetic field. We see this splitting of the M sub s levels, even though there's no magnetic field present. And it's characterized by two parameters, which are labeled D and E. And basically, this interaction follows a tensor, very much like what I said for or explained for the G tensor. And so we have similarly a tensor here, but we characterize it in terms of just two values rather than three principal values. It turns out for this interaction, you can reduce that down to two values, which are called D and E. And so if my tensor is isotropic, then it means that D and E are equal to 0. And this, of course, doesn't really occur very often in transition metals, but there are systems where this can happen. And in that case, then you basically don't have to worry about this zero field splitting, you see, because D and E are 0. If we have an axial system, then D is some non-zero value, but E will be 0. And for a rhombic system, then both of these values are non-zero, right? And so if you look here, the ratio of E divided by D will tell you whether this system is, how close are you to an axial system where E is 0, or a completely rhombic system where both values are non-zero. And so because of this ratio E over D is known as the rhombicity of the zero field splitting, right? And from the definition of D and E, you can show that this rhombicity parameter must lie somewhere between 0 and 1/3. So if it's 0, then I have an axial interaction, and if I'm at 1/3, then I have the maximum possible rhombicity, so the maximum possible difference between the values. Okay, so we can use this parameter then to characterize the EPR spectra of this type of system. And it turns out that the positions of the lines actually, if the zero field splitting is large, then the positions of the lines or features in the spectrum actually only depend on this parameter and not on things like the G values and so forth of the complex. So we can generate then a diagram which is known as a Rhambo Gram. And so here's the Rhambo Gram for spin equals 3/2. And along the x-axis, we have this rhombicity parameter, so this E over D. And then on the y-axis, we have the position of features expected in the EPR spectrum expressed as a G value, right? So if I know what microwave frequency I'm working at, I can convert an effective G value into a field value. And so I can use this diagram then to basically predict where the features will occur in my spectrum. And in some respects, this is similar to the diagrams for optical spectroscopy derived from ligand field theory that we heard in the last lecture, right? And so if I have a spectrum, I can then simply look across the x-axis and figure out, okay, where do I see features in my spectrum, and do they match with the expected positions, right? And so anyway, this diagram is called a Rhambo Gram. So here's just one brief example. This is also will be talked about in EPR1. This is myoglobin, which has a heme group in it, so an iron 3, which is spin 5/2, and it's in it's essentially a square planar environment in the heme ring, and so because of that high symmetry, the environment of the iron or the zero field splitting tensor then is axial, right? And so our rhombicity parameter should be 0. And so what you see in the spectrum is this very strong peak down around 1,000 Gauss or 100 millitesla at an effective G value of 6. And then there are some weaker features up around 2. Right? And so if we look at the Rhambo Gram for a spin 5 halves system, you can see that there are two features expected overlapped at G equals 6 from the plus minus 1/2 levels. And then in the plus minus 3 halves, there's also a transition which can occur at G effective equals 6. So we've got 3 possible transitions all occurring at the same place. And so we would expect a very strong peak as we see in the spectrum. And then there's another feature expected at G equals 2, but because that's only one transition, that feature should be weaker. And then up here we've got transitions at an effective G value of 0, which means that they would occur at infinite field, so they don't appear in our spectrum. And then there's a transition which at G equals 10, which is at very, very low field, and so we don't typically see that. So we can, from the shape of the spectrum and using the Rhambo Gram, we can see that our iron is sitting in a very, very highly symmetric environment, and that the zero field splitting has axial symmetry, or our E value is 0, right? And so if I have an unknown protein or metal, then I can use the Rhambo Gram for different possible spin states to work out, what kind of symmetry is the environment in, and can use this as evidence that I have, say a spin 5 halves or a spin 3 halves, and so on. Right? All right, so while we're with iron, just in the last couple minutes here, I'm going to touch on a common problem that occurs in iron-containing systems. All right, so this is a spectrum taken from a paper a few years ago where the authors were interested. They're looking at a quinone oxidoreductase, or NADH quinone oxidoreductase. And this contains a flavin, and they were looking to see if they could see an EPR signal from the flavin radical under certain conditions. And so they ran this EPR spectrum, and what they see is this nice peak at G equals 2, and flavin being a organic radical, you would expect then a sharp peak at G equals 2 with not much shift of its G values. So that all makes sense. But they also see a peak down here at G equals 4.3. And if you look carefully, there's something a little bit broader underneath this sharp peak as well. And these features are really typical of what's known as junk iron. So if I have an organism or a protein that I'm trying to isolate and there's iron present, it's common for iron to bind to the exterior of the protein in some undefined binding sites, right? And so if we look at the Rhambo Gram for spin 5 halves, right? So we have, which would be for iron 3. If you look for the maximum rhombicity, so out around, the right-hand side of this, you can see that there are 3 transitions which converge at G equals 4.3, right? And then there are a couple of other transitions down here close to G equals 2. And so this peak here at G 4.3 is really characteristic of iron in a somewhat asymmetric binding site, so where it has a high rhombicity. And as I say, is really common in many preparations. It's very, very difficult often to completely get rid of the iron, and so you're left with this, quote, junk iron signal, right? And so that's something just to be aware of, that if you are dealing with a protein that might have iron in it, if you see something around G 4.3, don't bang your head against the wall for days and days trying to figure out what on earth is this extra line in my signal or in my spectrum and so on. It's just a bunch of iron that you weren't able to get rid of. All right, so it looks to me like I'm basically out of time here, so I think I will just give a little short plug for EPR3. So what I haven't talked about today is what happens if I want to look at my system or system of interest at room temperature in a liquid solution. And that the spectra that you see under those conditions are very, very different. And essentially what we would see there is an isotropic G value in all cases, and we get splitting from hyperfine coupling. right? And so this is the spectrum of a nitroxide. And so what we're going to do is look a little bit at the issues that arise if I want to do a room temperature spectrum, and what we can see in a spectrum like this of a nitroxide. What do I see if I have a, say a copper complex or some other metal complex and so on. So anyway, this is in EPR3. We'll be looking at room temperature spectra, which are really quite different from all of the stuff that I've talked about in the lecture. And I'll explain why, and we'll see what we can learn from those types of spectra. Okay, so anyway, so here's a summary of what we went through. Hopefully I gave you a little appreciation of why EPR spectra look the way they do, what sorts of things we can get out, the G anisotropy and the hyperfine couplings, and what happens when we go to these high spin systems, and then don't forget to come to EPR3. All right, so thank you for listening, and I'll take any questions.
Questions for Art?
Up at the back, someone?
Yeah, you said that technically there can be lots and lots and lots of hyperfine interactions, but
Yep.
usually you don't see so many, so it's just that so many cancel out.
It's because the separation between them is so small, so you just get this complete forest of lines where, where the structure is just not visible in the spectrum. And that's actually a perfect segue to our next lecture, which is pulsed EPR, where Alexei is going to show us EPR techniques which allow us to take that, a system where you have that situation where the lines are not resolved because you have so many couplings overlapped and so on, and be able to actually pull them out of the data.
Any further questions? Okay, well, Art, you stole my introduction to Alexei.
Oh, well.